Hello, my name is Erkin Ötleş. I am a MD PhD student at the University of Michigan, and I'm here to talk to you a little bit about dynamic machine learning for medical practice. So the talk today is going to be focused on dynamic machine learning, specifically looking at dynamic machine learning in the context of healthcare. And we'll talk about why it's important to have dynamic machine learning. And then, after we do this overview, we will talk about a specific case study involving occupational injuries. And in this case study, we'll go over a formulation that we use that involves deep learning. So when I think about precision health and the way that we interact between patients and physicians and data, this is the graphic that comes to my mind, where we have the intersection of patients, physicians, and predictions. And I have physicians here in the lower left corner of the slide, but really any clinician or anybody that's part of the healthcare team can be counted in this blue bubble. I use physician because I'm training to be one, and also I like the alliteration. So the big focus is how do we get predictions that work well for patients and for physicians. And well, the first thing that we should do before we talk about how we get them to work well is we should establish a shared understanding of what predictions are. And this is the way I like to think about predictions. This rather simple equation where we have an input, which may be something that we know. In healthcare, this can be many different things like age, heart rate, medications that a patient is on. This information is passed to a model, and this could be a simple rule, it could be a machine learned model, it could be anything really. But once it's passed through the model, this model has to give you back an output. And this is a prediction that we would like to use for something. So you can think about this as, potentially predicting the risk of diabetes or the length of stay of a patient when they're being admitted to the hospital. Many different things that you might like to know with sort of limited information in the context of healthcare. So you put this all together, that's sort of my description of a model. So we have an understanding of what predictions are. And we're sort of in this context where we have patients and physicians, and we want all three parties to work together and have a shared understanding of the goal at hand, right? Which is to deliver the best possible care to the patients. Now, a patient might come to you as a physician and say any of the following things, right? They could say, I feel pretty good today. I developed this symptom last week. And then a physician might ask some questions like, well, when did this start? Or how long have you been on this medication? How are you doing in terms of your control? And all of these questions have some notion of time tied to them. But our model that we just talked about really doesn't have time, right? It has inputs and outputs, and it has the model itself. So shouldn't our models also have a notion of time? It's rather simple to inject it into the model, right? The formulation's right there. I added some t's to the y and x, and voila, we have indexed everything over time, and now it's dynamic. And so the concept is relatively simple, but the actual execution is a little bit more complicated. And we'll talk about a specific use case now, but I hope you can see why it is important that the models be dynamic. So now we'll talk about a specific implementation. And this is for a project that we've been working on for a little while, partnered with this company called Peers Health, led by a physician, Jon Seymour, and they're in the business of helping patients recover from occupational injuries. So occupational injuries are injuries that happen on the job. 3 out of every 100 Americans in the next year will be injured while at work. And this costs upwards of $60 billion just in terms of the insurance claims alone. The actual lost wages and economic detriment to the US economy are well over $100 billion per year. And this is not even quantifying the actual pain and suffering that all the patients experience when they are in the process of recovering from their injuries. So there is a significant incentive, both financial and in terms of the human need to get patients back to work as soon as possible and in the most effective way possible, because there's both dollars and human lives riding on it. So our goal in terms of occupational injuries is to predict the work status of patients over time. And this is over the course of their recovery. And the idea is that if you can do really good prediction, then you can use those predictions to help guide what treatments you might want to be able to employ to help get the patients back on their feet sooner. So we have access to a relatively large data set thanks to our partner peers. This data set has over 1.2 million patient injuries, all from a single Midwestern state in the early 2000s. So the geographic area is relatively similar, and all the injuries are extremely varied, right? These are all the injuries that one might experience in all the different jobs that a different state might employ, which is many different industries. But we have certain information that's shared across all these patients. We have their demographics, which are age, sex, job, and then we have observational information, which come in the form of claims. And these can include diagnoses, procedures, and their work status. These are all time-stamped over the entire duration of a patient's case. So if you were to take a patient's case and map it out over time, it might look something like this, where you have a patient who's a 25-year-old dairy farmer, and they get injured, and they have a series of treatments that come in over time, and then they return to work, and then potentially they leave work, right? So you have this trajectory where you have diagnoses, procedures, prescriptions, all observations are observed over time. These are potentially inputs, and then you have work status, something that you'd like to predict, as an output. So we have two sequences that we want to map to one another. And the key idea here is that we'd like to be able to make dynamic predictions like a physician would. So how would a physician think about this process? Well, one question a physician might have is saying, will this person be at work tomorrow, right? In a day's time, where are they going to be in terms of their recovery? And this doesn't have to be limited to one day. It could be, any number of days. And then the physician might ask, well, what do I know currently about the patient? What have I seen during their visit with me? What information have I collected? What do I know today? And they'd like to probably put that in context with what they have seen previously about that patient, what they know about the history of this patient, right? So the physician thought process essentially breaks down this sequence and puts it into a couple different components. And we'll use notation to denote the different parts of this process. So X of t is what we essentially use to label the observations. So this is the information that comes in on a given day, t. And so we have X of t, and naturally we should have Y of t. Y of t is the prediction that is made at every day. And then, well, what's the last thing that the physician was thinking about? The history. And the history is all of the observations that have previously been seen. And we sort of categorize all that as H of t. So we have three components, X of t, Y of t, H of t. And we'd like to build a formulation that's essentially a mapping of these X of t's to Y's of t's that also matches well with the physician's thinking. So there's a couple desired attributes that a formulation would have. The first one is that observations and history should both be used to make predictions. Then we should also make sure that the history that we're making is a good history, right? So then it should be an accumulation of all the observations we've seen up until today. These are relatively simple constraints, but they help ensure that the model works like a physician would think. So for the first constraint, mathematically, we can denote that as follows, right? Where the prediction is just a function of the history and the observation. And for the second constraint, well, you could say the history is just a function of the current observation and all the previous history. So now you might think, well, how do we implement this? Well, you can take a computational diagram and sort of draw out what the first equation would look like, having H of t and X of t produce Y of t, and then you could take the second equation, superimpose that, and say h of t, x of t should produce the next h of t. So there we go. We have an equation, but it's sort of recursive, right? We note that the outputs from a previous time step flow into the current time step, and then those outputs will flow out in the form of histories into the next time step. So we have this need for being able to pass information across time in a recursive manner. And luckily, deep learning has a framework that allows us to take advantage of this recursive framework in sort of an end-to-end differentiable format. And this is where we bring in the concept of recurrent neural networks. We won't go into too much details about these. Essentially, treat them as a black box for the majority of this talk. But if you have any questions, feel free to email me, and I have my email at the end of the talk. So can we just use a recurrent neural network? Well, unfortunately, our observations are very high dimensional, and we may want to be able to predict several different health statuses or things in addition to the health state that we are working on at the current moment. So we can't just use a simple RNN. And we'll talk about how we alleviate these with our formulation. So high dimensionality, well, you can take the variables that are high dimensional, like x of t and h of t. Observations may include things like diagnoses and procedures and medications, which can number in the thousands or tens of thousands of different types of diagnoses or procedures. And history, since it's essentially a concatenation of all of these observations, can be very, very high dimensional as well. So let's approximate these with lower dimensional versions of themselves and call these x tilde and h tilde, representing sort of approximations of x of t and h of t. And then we're doing a prediction task, right? So let's throw a hat on y of t. So then we've sort of modified our formulation to look like this, not too different. But then how do we take care of some of the things like the high dimensionality and the multiple task prediction? Well, we do this through our general architecture, which is a health state prediction model. And so that is displayed up here. We'll walk through that in sort of a quick couple slides. So we have the inputs. These can be age, sex, the things that we talked about. These come to the model through a transformation process known as the temporal transformer. We have a framework coming out for this that would allow you to take any type of longitudinal data, be it claims, EHR data, or even non-healthcare longitudinal data, and automatically transform it into a data set that's appropriate for this, and then also build the appropriate receptive model. And this information is then passed to ingestion. Ingestion takes high dimensional data and then brings it down into a lower dimension using a concept called word embeddings. We have a x double tilde of t, which is then passed to the middle. Middle makes a history representation, which is stored and passed back at the next time step. It's passed to final. Final will produce the final prediction, as well as any auxiliary predictions you'd like. Now, how well does it work? You might ask. We have an experiment that we did on patients that had an absence of at least 1 day. This is about half of our data set. We split this into test, development, and train, and then we saw how well the model predicts at every single time step. The predictive performance is relatively fair. You see an AU-ROC of 0.78, which is a measure of discrimination, and it's fairly good. The calibration, which shows how well the estimated risk matches the actual risk for the patient population, is along the 45-degree diagonal line, which is an indication of pretty good calibration. And if you'd like to be able to assess how well the model works on an individual, well, we have a little diagram here. And you can see that the model is plotting out over time the risk that is predicted for this given patient. At this point, where the black line came in, the patient actually returned to work, and you can see that the model's risks now are climbing, representing the model thinks that the patient should be at work. the model didn't actually know that the patient returned to work. So you can see that the model's risk is relatively well matched to the actual outcome for this specific patient. And so jumping through that, you can see the final graph there. Note that the way that we train this model is not designed to have a really superb individual predictions, but it's really meant to be a good tool for managing populations. It's designed for insurers or case managers to help manage many patients at one time. So there's lots of different ways to use this model. We showed you guys a health status prediction approach. There's ways to modify this in terms of the output so that it's an early warning system. Take a moment to wrap things up. So this type of dynamic work can be used in many different settings, from hospital-acquired infections to even helping hospitals deal with coronavirus and occupational injuries, as we just talked about. And the big takeaway that I'd like everyone to leave here with is the fact that all the other players in sort of the realm of healthcare, the patient and the physician, think about things in a temporal nature. And so that we need to make sure that our models, if they're going to interface with the patient and the physician, they should also have some notion of the dynamics of time so that they can speak the same language. And this is also that the patient, physician, and prediction can all work together well so that we have the best possible outcomes for patients. I'd like to thank you for listening to my talk. And if you have any questions, feel free to email me. My email is below. I'd love to hear your guys' thoughts at the session.